Let's look at graphing inequalities. Here's an example. You'll notice there's an x and a y in this inequality, which begs the question, what values of x and y might make this inequality true? Here's a random guess. Let's try x being 10 and y being 2. No particular reason, just to explore. If you do all the PEMDAS, work out the math, you end up with a true statement. 14 is greater than or equal to 12, and therefore this statement is true when x is 10 and y is 2. Here's another example. Randomly chosen numbers. Plugging in for x and y, doing PEMDAS. This leads us to a false statement. 3 is not greater than or equal to 12. One thing we can notice with this inequality is there are certain pairs of x's and y's that make it true and others that make it false. Our goal is to find all the ones that make it true. Here's a graph to represent them. Let's pick another random pair. Plugging in these values for x and y and doing all the algebra, PEMDAS not shown here, but it's done on a calculator, then what we'll find is that 14 is greater than or equal to 12, which is a true statement, and therefore that is a true point for this graph. I'll put a T here at that location to represent it. Here's another example. Randomly chosen numbers, x and y are 1. Plugging in, doing the math, this leads us to a false statement. -1 is not greater than or equal to 12, so that would be a point that makes the inequality false. And we could keep doing this. Let's do a couple more. Randomly chosen numbers, plug in, do the math. Oh, look, 13 is greater than or equal to 12. That is a true point. I'll put a T there for that. Here's another randomly chosen pair, plugging in, doing math, and we get a false statement here because 10 is not greater than or equal to 12. Now, this is not a very practical way to go about solving this problem. I just wanted to show you that there are certain ordered pairs that make it true, certain ordered pairs that make it false, and our goal is to find all of the true ones. Well, finding them all is going to be tough because there's infinitely many, as it turns out. Now, we could keep going all day long, and I didn't show any work, but I tested a bunch of different points, and I found out there were lots of points that made it true and lots of points that made it false. But you can see they've kind of fallen into a pattern. Mathematicians have discovered that there is usually a line that separates all the true points from all the false points. And I'd like to show you how to find that line next. Now, we don't much care about the false points. We only care about the points that make it true. It turns out the answer to this problem is the picture you're looking at here. It's a shaded region representing where all the points that make the inequality true are. But how do we find this line? Simple, as it turns out. Merely change the inequality into an equation and graph. Now, if you've reached this point, you already know how to graph lines. You can pause on either of these. There's the x and y intercept method. There's the slope intercept method. Feel free to rewind and look those over if you've forgotten, but this is where the line between the trues and falses is going to be. And then the next thing that we have to do is decide which side of the line all the trues are on. Now, we already know because we tried this problem earlier, but we're going to look at a more official way to do that. So what you do is you pick a random point and you plug it into the inequality to see if that makes it true. Now, I don't want to say 0, 0 is really random. It happens to be my favorite ordered pair to try. But I'm going to plug that in, do the PEMDAS, and oh, look, we get a false statement. 0 is not greater than or equal to 12. And so we know that the origin, or 0, 0, is a false point. That must mean all the other points on the other side of the line are the true points. And that's a quick way to find it by just testing one. Let's now explore what happens with the points on the line itself. Here's a point randomly chosen on the line, and we're going to take the inequality, plug that in, do all the math, and look what we get, a true statement. It is true that 12 is greater than or equal to 12 because they're equal. And what we've shown is that that particular point makes the inequality true. But mathematicians have discovered that if one point on the line makes the inequality true, they all will make the inequality true. And there's the answer to this. Now we see the answer to this problem. Now, what would happen if instead of a compound inequality greater than or equal to, what if we had a strict inequality just greater than? Well, let's test that same point on the line. Plugging in that same point and doing all the PEMDAS gives us a false statement. 12 is not greater than 12. A number can't be greater than itself. And therefore, that is a false point. But mathematicians have discovered if there's a false point on the line, then every point on the line is false. The way we represent that in mathematics, and by the way, the points underneath the line are still true, but the way we represent the false points is by just putting a dotted line instead of writing a bunch of F's on the line. And that would be the answer to the strict inequality. Let's take a look at one final example here. Here's an inequality we want to graph. Here's a graph to place the true points. Change our inequality to an equal sign. You'll notice here, graph the line, and then decide whether to shade above or below. Again, I like to pick the origin as a test point, so I'll plug in 0 for x, 0 for y, do all the math, and oh look, we get a true statement. 0 is less than or equal to 3, and since that's true, all the true points must be underneath the line. Remember, if this compound inequality were a strict inequality instead, then we would have a dotted line in our solution.